The example is x equals t, y equals 2/3 t to the 3/2, for t greater than or equal to 0. We've got the position vector, t comma 2/3 t to the 3/2. Notationally, by the way, this is f of t and this is g of t. And then the velocity vector is the derivative of the position vector. Its components are the derivatives of f and g, which in this case will be 1 comma t to the 1/2, 1 comma square root of t. The speed, which today, starting today, I'm also going to use a new notation for, cursive v of t, a slightly curved v, is going to be my shorthand notation for the speed today. That's going to be helpful to save time in writing, so I don't have to write the word speed all the time. Is the magnitude of the velocity vector square root of f prime of t squared plus g prime of t squared, which for this example is square root of 1 squared plus square root of t squared, square root of 1 plus t. The acceleration vector is the derivative of the velocity vector, which is also the second derivative of the position vector. Components equal to second derivatives of f and g. The derivative of 1 is 0. The derivative of t to the 1/2 is 1/2 t to the negative 1/2. So we could also write this as 0 comma 1 over 2 times square root of t. The distance traveled, whose dependent variable I'm going to be consistent with the book and call s. But keep in mind that when you read the book also calls this s of t. So the book uses the letter s both for a dependent variable and a function name. But I'm just going to use it as the dependent variable and call the function name dist. Now, I guess I could save time there and just call it d, but I'll keep it as a dist. Integral from 0 to t, speed of tau d tau. For this example, that's the integral of from 0 to t of square root of 1 plus tau. That's the same as 1 plus tau to the 1/2 power. To integrate that, you'll raise it to the 3/2 power and divide by 3/2. So you'll get 2/3 times 1 plus tau to the 3/2. Tau goes from 0 to t, giving you 2/3, 1 plus t to the 3/2 minus 2/3. You replace tau with 0, you get 1 to the 3/2, and 1 to the 3/2 is 1. 2/3 times 1 is 2/3. This does have the property that if you replace t with 0, you get 0. Note, distance at time 0 is 0. Also note, by the FTC, ds dt, which you could also call dist prime of t, the derivative of the integral is the function you're integrating. The derivative of the distance traveled is the speed. Use the same variable here, though, t. Don't use tau, because you want those to match. Okay, so this is stuff we already knew. What I want to do now is I want to write the acceleration vector in various ways. First in the abstract, and then for the particular example. The parametric curve itself looks about like this. So this is t comma 2/3 t to the 3/2. The curve itself does have equation xy equation, y equals 2/3 x to the 3 abs, but that equation doesn't have any motion implied because there's no time. It's the parametric equations where t is time that implies a motion. We know that at any particular moment in time, where maybe the location of the particle is right there, we've got a position vector, r of t, and a velocity vector that'll be tangent to the curve and have length equal to the speed. And we also know the acceleration vector is going to be in here somewhere. In fact, for our example, the acceleration vector always has a first component that's 0, positive second component. It's going to point straight up, no matter what t is for this example. So the acceleration vector might look something like this. I made it shorter than the velocity vector, but it could be longer. I'd like to understand this acceleration vector in relationship to the velocity vector. It is its rate of change, but I'd like to understand it more deeply. And also in relationship to, like, what's this angle between A and B? Dot products might be useful, for example. They are going to be useful. To start the process of doing that, we're going to define the so-called unit tangent vector. This is a definition. Capital T vector of little t is the normalized velocity vector, where normalized means find a vector in the same direction with unit length. It's the velocity vector divided by its magnitude, as long as the velocity vector is non-zero. As long as the velocity vector is not the zero vector. This is going to have unit length. Another way to write this is as the velocity vector divided by the speed. The magnitude of the velocity is the speed. I could write speed of t in the bottom, but to save time, I'll write cursive v of t. So it's a funny looking equation. T of t equals v of t divided by v of t. Capital T of t, the unit tangent vector evaluated at time t, is v of t, the velocity vector at time t, divided by v of t, the speed at time t. This also allows you to rewrite the velocity vector. Multiply both sides by the speed. The velocity vector can be thought of as the speed times the unit tangent vector. If this is the definition of the unit tangent vector, which it is, I can multiply both sides by the speed and get this equation. Yes, the unit tangent vector is a unit vector. You could verify abstractly that as long as you're not dividing by 0, this is going to have a magnitude of 1. The official abstract verification of that would look like this. Double absolute value signs within double absolute value signs. Or I could use a cursive v of t there. And then there's a property of magnitudes that scalars can be factored out with an actual absolute value sign. Let's write it like this. Scalars can be factored out like that, but this scalar is not negative, so I can get rid of those absolute value signs. And the length of v of t is v of t, the scalar v of t, it's the speed. This simplifies to 1. Capital T is a unit vector as long as I'm not dividing by 0. That's the official abstract verification of that fact. But to get toward our goal here, of understanding the acceleration vector, what we want to do now is we want to differentiate both sides of this. The acceleration vector is the derivative of the velocity vector, which better than be the derivative with respect to t of the right-hand side, the speed times the unit tangent vector. And boy, that should feel like I need to use a product rule there, doesn't it? Yeah, use a product rule there. Left d right plus right d left. Left is the speed. D right, I'll call a capital T prime of t. Left d right plus right d left. The derivative of the left is the derivative of the speed times the unit tangent vector. It's more traditional to write this in the opposite order. V prime of t times capital T of t plus V of t times capital T prime of t. I'm going to do something else a little strange next. With the second term here, I'm going to multiply by a disguised form of 1. The disguised form of 1 is going to be the magnitude of capital T prime divided by the magnitude of capital T prime. Like this. And this new vector that you see right here, I'm going to give a new name to. I'm going to call it capital N of t. It's called the unit normal vector by definition. Normal vector. Is it perpendicular to t, to capital T? Yes, it is, though that takes proof. Coming back to the picture, capital T prime is parallel to V and of unit length. Maybe that's capital T. Where is capital N in this picture? It is, turns out to be a unit vector, length 1. It is normal to the curve, perpendicular to it, meaning it's also perpendicular to the unit tangent vector, capital T. And here's one other thing that you can't really tell just by looking at it. It points in the direction that the curve is curving as you move. This particle goes along here. If you're driving a car along a road like this, you're turning to the left. The unit normal vector points in the direction that you're turning. That's capital N of t. And it is perpendicular. That's a right angle there. Why is it perpendicular? The reason is this. The norm of capital T of t squared always equals 1 squared. Because capital T is always a unit vector. Its norm, its magnitude is always 1. So if I square its magnitude, that's also 1. This is also capital T of t dotted with itself. If I differentiate both sides of this equation with respect to t and use the product rule on the left and simplify, I get 2 times capital T of t dotted with capital T prime of t equals the derivative of the right is 0, i.e. capital T of t and capital T prime of t are orthogonal or perpendicular or normal. They all mean the same thing. Perpendicular used by most people, orthogonal used most by mathematicians, normal mean used most by physicists. But all 3 of those words mean the same thing. And guess what? Capital N of t is the derivative of capital T divided by its magnitude. It's in the same direction as capital T prime. So if capital T and capital T prime are orthogonal, so are capital T and N. They're orthogonal too. So for sure they're perpendicular to each other. That doesn't, again, fully explain why it points in this direction to the upper left instead of this direction to the lower right, but it will. this can all be rewritten one more way at the moment. The derivative of the speed times the unit tangent vector plus, let me combine these two things. The speed times the magnitude of capital T prime of T, which is not necessarily equal to 1. Just because capital T has a magnitude equal to 1 doesn't mean its derivative does. Depends on how fast capital T is turning as you move, which is related to the curvature of the curve. Is it a small, tight circle, so to speak, that would have a high curvature, or almost straight that would have a low curvature? Times capital N of T. And we give names to these things. The coefficients of capital T and capital N. This is called A sub capital T. And this is called A sub capital N. This is called, in words, the tangential component of acceleration. And this is called the normal component of acceleration. And technically speaking, these expressions are one way to compute these things. Though, as you'll see when you do the reading, they're not the only way to compute them. And which formula you use to do the computation depends on the situation, depends on what's easiest to do. All right, let's have Mathematica compute these things and see what they equal in this example. The f of t, type things as fast as I can here, is t. G of t is 2/3 t to the 3/2. R of t has components f of t, g of t. V of t is the derivative of r of t. A of t is the derivative of v of t. Speed of t is square root of f prime of t squared plus g prime of t squared. Let's add in the unit tangent vector and unit normal vector into this. So this is something new. Capital T of t is tangent to the curve. It's in the same direction as the velocity vector, just normalized to have a unit length. V of t divided by the speed. What's the unit normal vector? N of t. Well, guess what? In Mathematica, I can't do that. It doesn't like just doing a capital N for a function name because capital N is reserved for numerical approximation. So what I typically do is I do none-it. What's that? It's not really none-it. It's n unit normal vector. What was the definition? It's right here. Capital T prime divided by its magnitude, which probably the best way to type that in is capital T prime of t divided by the square root of capital T of t dotted with itself. We could do the a sub t and the a sub n too, I suppose, here. I guess I won't bother with the subscript. I'll just type a capital T of t is speed prime. Right? The derivative of the speed, not the velocity. This is not the acceleration vector. This is a scalar quantity. And an of t, I guess I could type as speed of t times square root of t prime of t dotted with itself. Right? The norm of the vector is the square root of the vector dotted with itself. This should work. I'll enter it all, but how do you interpret it? What might we be interested in? We might be interested in, for example, graphing all these things and making an animation effectively of this picture. But it wouldn't look too much different as time went by than what you see here if I did that. So maybe that's not worthwhile. What might be more worthwhile is thinking about the a sub t and the a sub n, which are both scalar functions. The outputs of these things are scalars. I can graph them with an ordinary plot. I could plot, well, I could look at the formulas as well. What's a t of t? There's its formula. What's a n of t? There's its formula, kind of complicated. I simplify it somewhat. And actually, it could be simplified more because here I'd have a square root of 1 plus t squared. That could probably cancel with this one. But anyway, it might be handy plotting both of these functions. That might be informative. Make the AT of t red and the AN of t blue. That's the tangential and normal components of acceleration. What does it tell you? It tells you at the start, and the blue one's got a vertical asymptote, it looks like at t equals 0. At the start, the acceleration is made up of the red graph times the unit tangent vector, plus the blue graph times the unit normal vector. The total acceleration vector is very long when t is close to 0, because that blue graph's so high, it's got a vertical asymptote. And most of the acceleration is in the normal component, perpendicular to the curve. Yeah, if you plug in a small number into the acceleration vector, like 0.1, or even 0.01, or 0.001, look at that, it's a pretty long vector. Looks like Mathematica is saying it's vertical. It's actually not quite vertical. The first component would be slightly negative. Well, no, excuse me. I'm sorry. The first component is always 0. Never mind. It's always vertical, but long to start off with. The curve itself, when t is close to 0, has a tangent that's close to horizontal. The acceleration vector is pointing straight up. Most of the accelerations in the normal component, very little in the tangential component, causing the curve to curve a fair amount when t is small. You might say the tangential component being the dominant, the normal component being the dominant part of acceleration is what's causing more curvature here than over here. The graph is straighter over here. As t increases, you get to a point where the red graph's higher than the blue graph. The tangential component, the red graph, is bigger than the normal. When you're up here, acceleration vector points straight up. The angle here is a little less than 45 degrees. Most of the accelerations in the tangential component and less than the normal, affecting the speed and its increase more than the turning of the curve. Is an intuitive way to think about it. There are other formulas for these things that, instead of taking the time to derive, since we're already running low on time, let's just look at them in the book. And you want to use whatever formula is convenient. Here's the key box. It's page 669. The position function is r of t, acceleration function is a of t. Here's this decomposition. Call it an orthogonal decomposition because t and n are orthogonal to each other, with components a of t and a of n. What did we derive? We derived the fact that a of t is this derivative. That's the magnitude of the velocity vector there. That's the speed, derivative of the speed. It also happens to more simply be this dot product. That's simpler, isn't it? Let's check and see if that worked. Can I also compute AT of t as the acceleration vector dotted with the unit tangent vector? Yep, exact same formula. By the way, the formulas for the unit tangent vector and the unit normal vector, in general can be kind of complicated because you are dividing by square roots because you're normalizing. So there's the unit tangent vector. Probably the formula for the unit normal vector is even more complicated. Yeah. You have to compute that by hand, possibly. Maybe for simpler examples, can it be simplified? Probably. Yeah, a fair amount. Because you're normalizing, you're dividing by square roots, things can get complicated. But we did just see here, in these two lines, here and here, that this formula is giving you the same thing. For the unit normal vector, what did we do? We did it this way. But look, there's three other formulas for it. The simplest one looks like it's a dot n. In fact, these two simpler formulas are derived using projections. Geometrically, if you project a of t onto the line parallel to v of t, use the projection formula. This distance right here is a sub t, thought of as a positive distance. That's what that distance is right there. And if you project a of t onto the line parallel to the unit normal vector, then this distance is a sub n. So you can use projections to derive these formulas as well. And that's where those dot product formulas come from. And in the projection formula, the bottom of the fraction ends up being 1. I'm talking about the projection formula. B dot W over W dot W times the magnitude of W. The bottom ends up being 1 in these contexts because you're dealing with these unit vectors, capital T and capital N, to do the projections. That's why you end up dividing by 1. And you just get these components in terms of dot products, which can also help you figure out angles between A and these other vectors as well. Also notice there's no way for AT to be negative. The derivative of this, there's no way for AN to be negative. I said that wrong. AN can only be positive because that quantity can only be positive, never negative. AT could be positive or negative. This derivative of the speed could be positive or negative. The speed doesn't have to be constant. It could be increasing and decreasing. Its derivative can be positive and negative. It's positive when the angle between AT and T is less than 90 degrees, as it is in this picture, meaning you're speeding up, going faster and faster. If the acceleration vector pointing back this way and had an angle bigger than 90 degrees with the velocity vector, then you'd be slowing down. The rate of change of the speed with respect to time would be negative. AT would not be a positive distance. It would be a negative distance, so to speak. The component in the tangential direction of acceleration would be negative. But the normal component is always positive. It's always pointing in the same direction as the normal vector, which is always pointing in the direction that the curve is curving. Not just in 2 dimensions, but also in 3 dimensions. And you'll see 3-dimensional examples in the reading. And again, you can also compute whatever's convenient, AN with this formula or that formula. You can even use a cross product. How about that? I'm not going to derive these. The book doesn't derive them either. But you can check that they work in examples.